measures. Maybe take the top package, the whole thing. Yeah. Our performance measure of transfer functions. H2 norm, we define it as of transfer functions, for example, G. Okay, so the H2 norm is defined as the G2, and this is equal to the square root of the trace of the integral G transpose G dt. This transfer function G is in the S or the frequency domain. Okay, and this G is the Laplace inverse of cap G. So this is a time domain transfer function. And we showed that for a system like this, and measurement like this, the G2 norm is equal to the square root of the trace, again, of B W I showed only this, but in the homework we'll make you do this, okay? So you can be sure that it is correct. Okay, and then here where the W node is the observability gradient. And in many books you will see Gramian double M or 1M. And both of them are okay, because you'll see very top guys use 1M and 2M. Okay, so and we said that this gradient I can write it down as the integral of EA transpose C transpose C A to the A T dt, which is solution the Lyapunov equation. A transpose W0 A is equal to minus C transpose C. Okay, and then we set to calculate H2. For transfer function G. We can do it in two ways. We just use this equation, and from the system we have the B and the D, and then to get the W, the observability Gramian, we'll solve the Lyapunov equation. So we need the A and the C. So for this system, once we have the A, B, C, and D, then we calculate W0 from the observability Gramian, and then plug here to calculate the H2 norm. So we'll use A, B, C, and D to calculate W0, and then H2 norm. Okay, and in this process you can use the Matlab and command. Yeah. Or the second thing, number 2, we can use directly Matlab. So I'll form the G from the A, B, C, and D. And this using this command. G will equal to PCK A, B, C, and D. This is the pack command, and then I'll say use the H2 norm of what we have here. So that's the, this will give us the G2 norm. And again, we said that this is nothing but area under the G squared curve. G squared T versus time curve. And because we looking at matrices, so we sum all the G squares T. So we integrate over all the G's against the time. So this is area under curve. And we related this because it looks very similar to what we did in the LQG. Okay? So this norm can be a measure of performance of response of a system, X transpose QX, for example, for any system. Okay? So, when we get to the H infinity, we will drive this again so you can see how it relates exactly to the LQG. Okay, so this is what we covered last lecture, and then at the end, I start looking at H2 infinity. So now, before we do the H infinity, again, we'll go over the example that we did. This section that we're covering on these norms, you will never see in any book. Okay, done in this way. Okay, so you'll see cuts, pieces here and there, and I'm relating it also to Matlab, so you can calculate these norms. Oops. This example, if you look at the homework, the second homework problem that you just did, or the second exam problem, okay, you will see that I have two element rod, and the stiffness matrix will look like this. Okay, so so I have one element here, and then the second element, and the length is here is ½ meter. And this is node 1, 2, 3. And this rod has E, A of 1 Newton. So now the stiffness matrix, if you remember from the homework, it looks like this: EA divided by L, 1 minus 1 minus 1 and 1. This is the element stiffness matrix. And if this is 1 and then this is 0.5, so this result will be 2, 1 minus 1 minus 1 and 1. Now I assemble this and this. So when we assemble them, we should have, for example, F1, F2, F3, and then this is 2, because these two are the same elements, so this will look like this. U1, U2, U3. So that's 3 by 3. The first element will have 1, minus 1, minus 1, and 1. And then the second element between 2 and 3, so it will be here. So it will be 1, minus 1, minus 1, and 1. Okay, now I put the boundary condition. Boundary condition, 1 is eliminated. So I'll eliminate the row and the column. And then I have here 2 by superposition, minus 1, minus 1, and 1. That's what we have here. 2, minus 1, minus 1, and 1, times 2, which is this 2. And the same for the mesh matrix. So now we have this system has stiffness and mesh matrices. I want to form the A matrix. So the A matrix of the system, I take the second order differential equation and transform it to a set of first order differential equation. So we don't need this. So we have mx double dot kx is equal to little b and the force, and then we transform this to first order system. So I'll take the inverse of this, so I have x double dot, and then I'll take this to the other side, so it will be minus m inverse k minus m inverse b 0 and f. Then we write it down in the state space. So we'll have x1 and x2 dot dot x1 and x2. And then I have here 0, m inverse b 0, and then we have here 0, identity minus m inverse k and 0. So that's what we have here. That's what we have. I added here damping for the system. So the damping in this case is proportional to the stiffness matrix. Okay, so now we have this is Z is a 0, and then identity matrix E minus M inverse K minus M inverse times the damping matrix. This is the B0 multiplied by M inverse. So we have the capital B, and then we only measure this last parameter, which is C is equal to 0, 0, 0, and 1. Okay, now the H2 norm, I'll follow the first one. We have the A, B, C, and D. I calculate the observability gradient by the solution of the Lyapunov equation. And then take this and put it in the equation for the H2 norm. And in this case I have 0D, so I don't have the second term. Multiply, get the trace under the square root. This would be H2. Or use directly this Matlab command. So we pack and then get the H2 norm. And the result, as I showed you last time, is this. So for this example, we get the H2 norm either by the first method or the second method, and these two are the same. Of course, this command is nothing but the solution making program of the first equation, set of equations. Okay, now we'll go to the H infinity norm. Again, of any transfer function G. So this is, again, looks like this. And physically, this is called the maximum value of G in the frequency domain over frequency bandwidth. And so this you can say something like this. Actually, this is written more precisely like this. Again, over omega. And this is the supremum operator, which means the least upper bound. And this is nothing like this. It looks like this, you know. So this is omega, for example, and this is the transfer function of the system. This the soup of G, magnitude of G. And this is the magnitude of G. So it's not exactly the maximum, it's slightly above the maximum by the tolerance limit that you can put on your solution. And as we'll see, when we will try to find this, I have to find it by an optimization method. So any optimization method has tolerance. Where would you hit the maximum? So we will say it is the least upper bound that we can find. Okay? But nonetheless, it is physically, it's the maximum value of the transfer function over certain frequency band. To get this, we will define this least upper bound as gamma, as a parameter gamma. And I'll leave this for a few minutes until we looked first. We did some summary of the Hamiltonian matrix. And let me just make here one little thing here, squeeze here. Standard Hamiltonian matrix. And this standard Hamiltonian matrix appears in the LQR optimization. And I will put this in the notes without, I'm not going to drive it here on the board, but you will see the proof in the notes. And in the notes also that I just gave you, I have the proof of the inversion lemma. Okay, so if you look here, after these two graphs, or after these two figures, I put here the proof of the inversion lemma. So you will see how it is done. I told you just multiply both sides by certain matrix, then do the manipulation, so all the details are here. Okay. And we'll do the same for this Hamiltonian matrix. We'll just show you how it appears when we try to get the optimum gain of LQR. Okay, so we said here we have A minus Q minus A transpose, B or inverse B transpose, X and Y. And the solution of the Hamiltonian system of matrices gives, of course, the X and Y. And from the X and Y, we can generate this. I showed in the handout that I gave you how to calculate this, how to calculate these two numbers. We will not calculate these exactly. We will calculate from the eigenvalues, eigenvectors of the H matrix. We calculate two matrices corresponding to the stable eigenvectors, and then from this we showed that they are equal to this. Okay, and you have the proof, but nonetheless, that's what we need. We take this system, solve it somehow, calculate these two matrices, and from these two matrices we calculate this new matrix, which is the solution of the Riccati equation. A transpose P, okay, plus PA minus P B R inverse B transpose P is equal to minus Q. This is the standard Hamiltonian matrix. We will form another non-standard Hamiltonian matrix which appears in the H infinity optimization. Very similar to this. If you follow exactly the same procedure, you will come up with the non-standard Hamiltonian system of matrices. And in that non-standard, this term appears. Anyway, we have this. And then we said, once we have P, then we can go and calculate K of the LQR, which we used it also in the LQG, exactly the same. Because we said the controller and the Kalman filter design can be separated completely, and I can use the same approach to calculate the gain for the LQG, and this is equal to R inverse B transpose MP. Or, now this is R inverse B transpose Y and X inverse. I showed now two properties of the Hamiltonian. The first one, we call this matrix H, and this Hamiltonian is this matrix H. Hamiltonian matrix. We said that the H has its eigenvalues appearing in pairs. Plus or minus lambda. Okay, so some of them are stable, and the complement values of them are unstable. Okay, and we proved this last lecture. And then at the end, we said here the stable eigenvectors, stable eigenvalues corresponding to stable eigenvalues of the closed loop system. Stable. Said, for example, if lambda I is eigenvalue of H, and the corresponding eigenvectors are, the corresponding eigenvector is, for example, xi, yi. Then I can write the eigenvalue problem for this system like this. equal to lambda I, xi, yi. This x is cap x, which is the matrix here in the Hamiltonian system. Okay, now I'll expand the first row. Expand the first row. So we'll have lambda I, xi. This is again cap xi. Will equal to A cap xi minus B R inverse B transpose yi. I'll replace yi from here.
Is that a negative B or a negative 1B2?
Yes, ma'am, negative. Yeah, this is negative. In the non-standard form, it will be positive. Okay. So now here, and we expanded the first row, so we have lambda I, xi, and then A, xi minus, and then yi. Yi, I can replace it from here by P and xi. So I can replace this now by P and xi. And then we have all this, one group, which is this. And then this xi and this xi, I'll factor them out. So I'll factor this out. And the term between brackets becomes A minus bk xi lambda I. So now this is an eigenvalue problem. This is the eigenvalue, the eigenvector of this matrix, and this is its eigenvector. So now from the Hamiltonian matrix, the values that are eigenvalues for Hamiltonian are also eigenvalues of the closed loop system. The closed loop system, I wanted to select the k to make it stable. So the eigenvalue of this matrix are the stable eigenvalues of the H matrix. The bottom line now of all this, because I have H as positive and negative eigenvalues, I want the eigenvalues of the closed loop system to be deep inside the S-plane, negative side of the S-plane. That's the stable ones. The unstable ones will be way out here. So which means none of the eigenvalues, positive or negative lambda, will lie on the imaginary axis. They have to be deep inside the left and the right hand side. That's what we will need to drive the G infinity node. So now from all this, summary of all this, and we'll see here as the eigenvalues of the closed loop system must be deep inside the left hand side of the S-plane. Then this implies that none of the eigenvalues of the Hamiltonian lie on the imaginary axis. Okay, now the non-standard this is one form. And then in the homework, we'll give you 2 more forms that will converge to the same result. This is not unique, non-standard form. We have A minus C transpose C over gamma squared B transpose minus A transpose. X and Y. We can have gamma squared here, and here is C transpose C, or we can have C transpose C over gamma, B transpose over gamma. All these will give the same result. Now from this we can extract the corresponding Riccati equation. Exactly like what we've done here. So now from above system, we can extract the corresponding Riccati equation, and this will also be non-standard Riccati equation. So how we did this last lecture, I took the first equation alone, expanded the second equation alone, and then now, so here we'll write x dot, y dot alone. And then we write the expression for dy x inverse by dt. Okay? When we do this, then we need to do the first times the second plus the the derivative of the first times the second, plus the second times the derivative of the second. And then we extracted this from here, x and x inverse d by dt is equal to 0. And from this, because this is identity matrix, or this constant, so its time derivative is 0, and we extracted from this that d x inverse by dt is equal to x inverse dx inverse by dt, and x inverse, and we have here minus. Now, again, we have P is equal to yx inverse, which is this term. And if we limit ourselves as we've done that the P is constant, so this will equal to 0. Now I have y dot, I'll replace it from here. And this is nothing but x dot. So I'll replace this from here. So we'll expand the first equation here, second equation here. Use this identity plus this identity. Plug x dot from here, plug y dot from here. The result will be A transpose P. P and A. Okay. Plus, if you look at what we have here, these terms plus this sign are here. Okay. Now I have here B and B transpose. here I have B, R, B transpose, and I have P and P. So whatever I have here, pre and post multiply by P. So I'll have here plus P, B, P transpose, and P. And on the right hand side, minus Q is minus Q. So this will be, instead of this, we'll have, as if this is Q, so this will equal to minus C transpose C over gamma squared. This equation has solution in Matlab. This equation has solution in Matlab. I can extract P directly. As we have in the notes, I have P, and then the A's and B's are, and the R's and the Q's are everything known. This is linear in P, quadratic in P, so we have algebraic Riccati equation solution, ARE. ARE, algebraic Riccati equation. Because algebraic, because dP by dt, we put it equal to 0. It's not time dependent, it's only algebraic polynomial. So the algebraic Riccati equation, this will give us P, and I have to give it here the A, the B, the Q, and the R. This is in the notes, okay? If you look in the notes back, you'll see this. This command, I cannot use this command to solve this. Because this is non-standard Riccati equation. Because of this plus sign. Because of this plus sign. Okay? Now, how we use this to calculate the infinite norm of the transfer function G. I'll rearrange this equation like this. Minus A transpose P minus PA is equal to C transpose C over gamma squared plus P, B, B transpose, and P. And then redo this like this. SI oops. So I added and subtracted the SI. Okay. Here, because the transpose. Huh?
It has a negative sign.
Yeah. So this is the transpose of it. So the complex conjugate when I have I omega. So this will take care of the negative sign. Okay. So this is the complex conjugate operator. Okay, now I'll say here let phi is equal to, as we did last time, SA minus A inverse, then phi inverse is the SA minus A. and then I'll pre-multiply and post-multiply. By V transpose, phi transpose minus S and B T of S. Again, when you do the transpose operator, you replace the S by minus S. Okay, so pre-multiply and post-multiply these two. So the result will be like this. B transpose, and I'll write only now the phi without the argument, okay? But now it's implied, huh? So this is phi transpose, and then that's the pre-multiplication, and then times this. So this will be minus, will be phi inverse transpose, okay? And then P, and then we have the phi and B. And then the second term will be here plus B transpose, phi transpose, P, phi inverse, phi and B. Then the right hand side will equal to B, phi transpose, C transpose C, phi and B over gamma squared, and then the last term, P, B, B transpose, P, P and B.
So Dr. Parasteso should be plus, not minus.
This is plus, yeah, so. Okay, now, from here, this will cancel out. And this will cancel out. So we'll have B transpose, P, phi and B, B transpose, phi transpose, P and B. Okay. And what we've done last lecture. And I will say here if G is a transfer function. Of this system. Then the infinite norm, let me take this out. Then the infinite norm is the supremum operator of magnitude of G. Taking over frequencies, band. And we said this is in effect it is the least upper bound of magnitude of G. And we looked at methods for calculating the infinite norm. We said the first method Matlab. And we have the A, B, C, and D, and then we'll calculate G by the pack command. And then we go and calculate H infinite number using this command. And the second method we said we'll use the Hamiltonian matrix. And the Hamiltonian matrix can take one of these forms: A minus A transpose, B transpose minus C transpose C over gamma squared, or B transpose over gamma squared, C transpose C minus A transpose, or B transpose over gamma minus C transpose C so check the B transpose over gamma and minus A transpose. And in the class I did this first case. And from here we extracted the non-standard Riccati equation. And this was the A transpose P, PA plus C transpose C over gamma squared plus P, B transpose P is equal to 0. And we said the main difference between the non-standard and the standard is the sign. This is plus. If this is minus, then we have the standard Riccati equation. Now, we can solve the standard Riccati equation, but we cannot solve this directly. So, to solve the non-standard Riccati, we use Iterative Approach. And why? Because we don't know what this gamma is. And we said here where gamma is equal to the infinite, I'm sorry. Greater than the infinite norm of G. So now here, the objective now. Find the least upper bound of G. And we find it such that pardon? No, we said G transpose G is less than gamma squared. Then, okay, so now we find the least upper bound of G such that we have the following. Number E, gamma has to be positive number. And then number B, the Hamiltonian matrix H does not have eigenvalues on the imaginary axis. So now I will input the A, B, C, and D matrices, and then input an initial guess. Of gamma, and then I go. I form the H matrix. Now we have the H matrix, then I go and calculate the eigenvalues of the H matrix. Then now I check if any of these eigenvalues have real part is equal to 0 or lies on the imaginary axis. Is any real part of the eigenvalues is equal to 0? And if it is no, then we're done, minimum. And if not, then reduce gamma and go here. So the main objective of this is. Pardon?
Which of them is no?
Oh, this is the no. This is the yes. Is any of these no? Then we're done. Then if it is yes, then we reduce gamma. We don't want anything to lie on the imaginary axis. So now the main purpose of this, minimize gamma.
I thought if it said no, then you go.
Pardon?
I thought if it said no, then you reduce the gamma, because if it's not as close as it could be to the imaginary axis, you're going to do something else. I thought that the object of this loop was to move the eigenvalue.
Yeah. Yeah. Okay, let's say let's make here this. We want the absolute value of this within certain tolerance to be on the Is that correct or not?
Doesn't that depend on if we are increasing gamma or decreasing gamma? If we are approaching from the upper bound, so actually we are seeking when it starts to get to zero. So it's
When it starts going to zero.
So the original setting was the correct one, which is if it's no, then we're done. Then we reach the minimum.
Yeah, it's correct. We will always begin with very large number. Yeah, it's correct. So this is no, and then yes, and then we'll make this input gamma very large. And this, as I was saying, because we cannot home on the zero exactly, so we'll say the absolute value is less than very small tolerance. Okay. Now, in the handout that you have,
Yeah, and the note is the opposite case.
pardon?
In the note is the opposite case.
Then it's in my typing.
Okay.
Yeah, corrected because this has to be correct. You know, like if we are with large values, then we are in the negative axis. If we reduce it, we'll reach a point when it becomes very small, then they will be on top of the
The real
axis.
part close to zero.
It will be very close to zero.
Right, so if that real part equals zero, then if it's true that the real part equals zero, then you've gotten to the minimum, right?
It says when the real part is equal to zero, that means it has reached the imaginary axis.
Yeah, so it's very close to the, yeah, so
So it
this,
should be opposite.
okay. So now if it is very close, then we are okay.
That's
So
good.
it's yes.
Then it's yes. Yeah. And then this should be no. Let's see the notes. Yeah, so the notes are okay. So I'm typing very fast, you know, so I can catch up the lectures. Okay. And also, you know, like this. Subroutine. I don't need all this. So here you create this file, for example, funh.m. So in Matlab, you go and new, and you create this file. And this file will have the following. The first line is function line. And then this function is the function f, and then it has constraints g. So this is the function and the constraint. And this function is equal to, it has this name, function of h infinity, and then it has the argument x. this argument is the variable that I am varying. And this variable is gamma. Okay? And now I go in, I define the system matrices, the A, B, and C. And then now I use this form. A, B, B transpose minus C transpose C, gamma squared minus A transpose. Okay? And then now I'm going to calculate the eigenvalues of H. And then I break it down to, well, I just got the real part. So the real part of H and get the absolute value, and I call it RE. Now, if RE is very small, which means it's on the imaginary axis, I'm going to make a counter CO is equal to 1. And if this counter is 1, I'm going to make the function value very, very large. So if I am on the constraint, I'm going to make the function value very large. I'm trying to minimize, so this automatically will exclude these numbers. Now, otherwise, if it is not on the imaginary axis, the function value is equal to the gamma. So this F is equal to my gamma. Now I'm going to put here, so this is all done, and I define the function value. I'm going to put here the constraint. Now gamma has to be greater than 0. The constraints in Matlab optimization takes this form. It's less than 0. Then now to make this look like this, I'm going to multiply by minus. So this is equivalent to minus gamma is less than 0. Or G is equal to minus gamma, and gamma is the x, so this will be minus x. So now I put the constraint, and I have only one design variable, which is gamma. I want to minimize the gamma, and it is a design variable because the H depends only on gamma. So the only variable that I am varying is the gamma, which is my design variable, and at the same time is my objective function. So now this is the constraint. If I have design problem that has many constraints, then I have G1, G2, and G3, and so on, and I have to put them all in this inequality form. It has to be in this form. Now we're done from this. Then I go and in Matlab now, this routine is over. Now you can save this routine under this name. And then you go and input initial guess. So we are in Matlab now. I put an initial guess, x, 0. And I put a very large number, 1 e to the 6, for example. And then I'll go back to Matlab. And then I calculate the x. This will be equal to this command, use constrained optimization program or subroutine in Matlab. This is Matlab command. And I applied it to this function. Oops, I'm sorry. And then comma, starting from x0. So this is Matlab command, optimization command from the toolbox, optimization toolbox command. There are many other and many other routines, like minimization was simplex method and so on and so forth. So the bottom line is I start from an initial guess and then put the X that I improved the design from an older design based on this function value routine. And then once you do this, then it will give you the optimum value of the gamma. If you have a nice well-behaved function, no matter where you start, you will end up with exactly the same number. If you have bad function behaved, then you have to try different starting point and find the absolute minimum of all of them. So you can get the global minimum. In this case, because it is quadratic, we are solving Riccati equation, which is quadratic. So the solution is very fast and it converges to the same optimum. So now this number should conform exactly, the output here should conform exactly with what we get if we have this command G. Okay? So these are now two methods for calculating the H infinity. We'll do two more now. And this approach is what is used to calculate this H infinity norm in Matlab. If you look at the H infinity M file, then you will see very similar approach to what we have.
I guess the H infinity norm assumes you're working with a quadratic function.
Pardon?
I guess the H infinity norm assumes you're working, I mean, that command assumes that you're working with.
Because the Riccati equation is quadratic. Let me show you the third approach, because we will not go in detail in it because it's not a good approach. In the handout that you have, you will see the approaches that we have. Matlab, the H infinity norm, and the Hamiltonian approach, and then the frequency response approach. Frequency response, I come and define the frequency range that I'm interested in. So I'm going to use the log space. So I'm going to have 200 points to evaluate the response added. And these points are spread from 0.1 frequency to 10. So I'm covering the range between 10 to the minus 1 power to the 10 to the 1 power, okay? So that's the frequency range that I'm going to cover, from 0.1 to 1, 200 points. Then now I have the A, B, C, and D. I can calculate the numerator and the denominator using the state space transformation. I have the numerator and the denominator, then I plot body diagram. Body diagram will give me magnitude of the transfer function. Now, I had here in the beginning of the class G infinity norm is equal to this norm is equal to the maximum value of the magnitude. So you plot the magnitude, and this is the frequency, and then this is the magnitude, and the absolute value of G and the maximum value is my supremum, or which is also the maximum value of G over omega. So this is one definition of G infinity norm. The second the G infinity norm is less than gamma. The third that we did is the H infinity norm. I can calculate it from then now the last method that requires some doing is this. So the last definition is this definition. Is equal to sigma max of G, which is the maximum singular value of G. So this is what we're gonna show right now. Because in the derivations of all the different rules of H infinity, we will need this method. In the formulation, it's done by the Hamiltonian that has the gamma, so you can relate all these different methods together. Okay. So the last method is and again, if G is a transfer function, then we can use the singular value decomposition, and the singular value decomposition is given the acronym S, V, and D. We can use to put it in the following form. So we have G is equal to this is very similar to the model decomposition. If you think of any matrix, I can put this matrix in its eigenvalues and eigenvectors, eigenvector matrices. But if G is a square matrix, then U and V are the same. If G is a rectangular matrix, then I have left and right eigenvectors. And this is no longer a square matrix. If G is rectangular matrix, then this will be rectangular matrix. Okay, so now, for example, from here I can, and also this is the matrix of singular values, and then the U and V are made as we've done in the model decomposition, and they make them unitary matrices. And this word means such that U is equal to identity and V, the asterisk operator, is the complex conjugate transpose operator. Okay, now if we do this, then now I can write G transpose. If it has complex number, I also inverted the complex number. Then G transpose G is equal to U. And then the G transpose, I'll flip all these. So I have V, a singular value, they are real. So this is transpose, and then we have U. Because of this characteristic, then this will be identity matrix. Okay. And so this will equal to this matrix will look like this. Zero, 0, and 0. And it has here sigma 1 and sigma r. Diagonal matrices like this. So this part is a square matrix, and the rest of the rectangle are zeros. Now with this is like this, then when I take the transpose, then I have also this part is here, and then this part is here, and then this stays as it is, sigmas. Now these V's will look like this. And I'm calling this V1 and V2. And I'm going to partition this. And this part is corresponding to the multiplication with this part. And the V2 is corresponding to the multiplication with the zeros. And then now this side, because they transpose, I'll break it down to two pieces. This will be V1 and then V2. When we multiply, so we'll have G will equal to V1 sigma 1 squared sigma r squared V1. Suppose and, everything that multiplies the V2 will go to 0. Now, from here, I'll expand this V1, and I'll expand it like this small vector V1, VR. same for here. V1 and we expand again this, so I can have V1 and then sigma 1 squared and so on. And I can write that this is definitely less than the maximum value of these sigmas times the vector squared. So this would be definitely less than sigma max squared. V1. If we selected a V such that this applies, when we take this as V1 and V2 times V1 and V2, V1 and V1 transpose, V2 transpose, then this is the identity matrix, then this would be identity matrix. And this would be less than sigma squared. Then now the final result is then this will say that G is less than sigma max squared, which is very similar to what we had. G transpose G is less than gamma squared. Then sigma max. Okay, so the whole thing is we need this matrix because this matrix has all the sigmas and we need to find which one of these is the maximum. So I have to calculate this number. So now to calculate sigma max, we'll go in Matlab. And we'll say, for example, sigma is equal to SVD of G. If we need this and this, we can write them also here. So for example, if you need the unitary matrices, you can write them in the full description. And we'll just make here a couple lines because this is not the whole story. Okay, so we'll say now for U sigma and V asterisk, use U, for example, sigma and V, and this will equal to singular value decomposition of G. To make the story complete, this G, if I leave it like this, then it has the Laplace operator or the frequency. So I have to first calculate this G at every frequency. And then I put the corresponding G here. Then the matrix, everything is known. Then I can apply on it the numerical calculation of the singular value decomposition. What is the singular value decomposition? It is half this matrix. Half this matrix. This matrix, if I have G square matrix, then this matrix is the eigenvalues of the matrix. So this, if it is a square, then I have sigma squared 1, sigma squared 2, and so on. So if it is a square matrix, this is my eigenvalue, my eigenvector matrix. This is the transpose of it. This is the matrix of the eigenvalues. If it is a square matrix. If it is not, then only the square part will appear, the rest will be filled with zeros. So for example, this can be 2 by 2, and then the rest, if it is 2 by 8, then the rest is zeros. Okay, so now how to implement this? I have to first calculate the G at every frequency. I have to calculate the transfer function at every frequency. So to do this, I define the frequencies, the frequency range. And then now I have the G, then I take the G and the frequencies and calculate the frequency response. This command, frequency response, is Matlab command, will get us the frequency response at all these frequencies. Now I go calculate the singular value decomposition of this matrix that is everything is known in numbers. Then I can extract the right hand, the left hand, the right hand vector. The left hand eigenvector, eigenmatrix, the right hand eigenvector matrix, as well as the singular decomposition matrices. Now I'm going to store these in an array. This is because this case is very simple, because I have single input and a single output. I have single input, single output. If I have more, then I have as many singular values as I have combination between sensors and actuators. In this case, this is, I have singular value, because I have single input, single output. Now I can store them in this array. Now I can plot this array as function of frequency. I can plot it as function of frequency. So now the result will be something like this. This is the singular value, sigma, again is frequency. I'm going to have something like this again. I want to find the maximum singular value. The maximum singular value, again as we showed, it's equal to the maximum amplitude of G, a function of frequency, is equal to the gamma, is equal to the response that we get from the system. Now, the examples that you have shows all the comparison, and in the handout that you have, I give you the D's and the C's and so on in the program. You can try it and see the comparison between all of them. I think we've done this fairly good detail, so now we have to, where are we going to use all this? Okay? Where are we going to use the comparisons?
But you have XO equal 100.
You can have what?
It has XO equal to 100.
XO? I just put this as a guess.
Yeah, I thought you said it was like 1 to even 6 or something.
Because the value that we get here is like 6 or 7, so I know ahead. But if you don't, just make it 10 to the 6. Try any number and you will converge to the same value. Now this section added to before this. Okay, the handout that I give you right now is an appendix that adds to appendix 1 and 2. This is appendix 3 that you just got, and then add this to the main part of the text. The first 3 pages I will not explain now because these are self-explanatory. How to implement the LQG using Simulink. Okay, and I'll begin at the last couple pages. Here is the here I have a general block diagram, and we'll make this later on in a special form. Look, in a special form. So here first, I have the controller and the structure. And please, in the handout, make this little w, because I made a D, and we wanted to conform with the things that we've been doing. This is Y reference. And then here is the output Y. The output that I get, also please make this, instead of N, make it little v, and this is my noise. This is my disturbance, as we used it with the LQG and LTR. And then this is the system output. Now the difference between the output and the reference is my error. I multiply it times the control gain and generate the U. Okay, so we can write, for example, that Y plus the noise, and then this whole thing is minus YR. This is equal to my error signal here. Okay, and then I multiply it times K will give me U times G will give me the output here times the disturbance will give me Y. Then Y will equal to the disturbance plus the E times the E, which is Y now I'll clean this and bring Y to this side. So I have I plus gk times y, gk yr minus gk times m v, I'm sorry, and then w. And then I'll extract y by looking at the inverse of this. And if we look at scalar case, then I can write gk I, this is equal to plus gk. So this, if I can look at what we have here, then as if I have here gk with the unit feedback. This is an ideal scalar case. So what I have here is in effect a transfer function. And I'm going to call this transfer function t. Okay? Now we come here, and this look the same like this. So this is t yr minus t and v. The last term doesn't look like that, but I'm going to call it S, cap S, and W. If we look at t plus s, t again, if we have it like this, gk 1 and s is equal to then I can factor the denominator. And the numerator becomes, and the sum of these two is equal to 1. Okay, so the sum of t and s is the same. So if I want t to be small, then s has to be large, and vice versa. Okay, now let's look at this. Here, this is known. This is known. And what we're trying to do is find the best K, design K. So now, as G is known, then our objective is to find or select K. So how would we select K? Any value that I select will affect this, because it affects this, and affects this. So now we have disturbance. We have noise in the sensors. And then I want to track a certain command input, or reference command. My output that I like to have, I like it to track this without being affected by the noise or by the disturbance. So I want to do two things. I want to reject the effect of the disturbance, and I want to reduce the effect of the noise contamination. These are the two goals that I like to do. So now, objective is to select K such that we have disturbance restriction and also if the effect of the noise contamination is minimized. Now if I want to reject the disturbance, means make this very low. And when I make this low, then this becomes high. T becomes high. When T becomes high, I amplify the noise. So there is one is pushing and one is pulling. If I make this small to make this very small, when I multiply small number by any disturbance, this is reduced. But when I reduce this, I increase this, and I amplify the noise. So now there is one is pushing and one is pulling. So now these two requirements are contradictory. But again, thank God, the things work for our favor. Okay, let's look at we have, this is the frequency, and the frequency this is disturbance. Usually the disturbance is low frequency and the noise is high frequency. So we have here a zone which is the disturbance. And then I have here a zone which is the noise. So I like to select the K to shape the S and T to do these two functions. So if I want to reject the effect of the disturbance, I want at low frequency S to be very small. So S should look like this. And this number is 1 or 0 dB. This number is 1. And this axis will be absolute value of S. And then now, this to reject the disturbance. So this will give me disturbance rejection. And to have noise rejection, I have to have the T, the reverse characteristic. T will look like this. Now when I add these two up, this is 0 at this high range, and then this is 1. And then this is 0, and then this is 1. So when you add these two up, I should have 1. So now when we add these two, then they should be like this. Or on the, if we do it dB, then it should be on this axis. Okay. Now, how would we have this curve or this characteristic? We look at the excitation that's acting on the system. And then we draw this curve by ourselves. We make a curve look like this. How? We'll show you how. Okay? And then here, I know where is the noise range, what frequency range. Then I try to shape the T curve like this. Now we said S is the sensitivity to load. T is called co-sensitivity, or because T and S is equal to 1, this is sensitivity, and this is called complementary sensitivity, or co-sensitivity. So this is co, or complementary sensitivity. Next lecture, we will reshape this graph. I will take here some boxes, multiply them times some frequency function to bound the S and the T with special shape that we like to have. So good evening, and I'll see you Wednesday. So accordingly, these two are contradicting objectives. Okay. To erase all this and do it again, but I'll erase this apart. And then we said here ideally so this is the frequency. Plot here the absolute, the magnitude of S, the magnitude of T. And then define two things. I want S to be as small as possible, and I'll do it so I can reject the excitation. The excitation is usually low frequency, so the excitation looks like this, maybe, a plot like this. Everything that excites the system falls in this frequency bandwidth. Then now, I have have to make this smaller. So when I multiply it with this number, the result will be almost 0. So I have to make this something like this. So this is my S. And this is in dB, so this is 0 dB. Okay. The reverse in the case of the T, I have the noise is usually high frequency, so it lies in this regime, and I have to make a T look like this. So here is the noise. And then here is the excitation. And this is T. Okay. We want to look in another plot like this, but in terms of the control gain K. This in 3 steps. If you look at the output is affected by 3 requirements, or 3 things. The output has to follow the input. So this output has to follow this input. So in vibration, I have to make this and this 0. They have to be equal. They have to be equal. So this number has to be close to 1. Has to be close to 1. But if I make it close to 1, then the noise will be very high. Okay? And if I make this close to 1, then I satisfy the disturbance restriction. Okay? But if I look at this equation, T, I can rewrite T. And I'm going to rewrite it for the purpose of tracking or regulation. I want to have y equal as close as possible to yr. Okay. So now ST is equal to GK. I'm going to rewrite this like this. G 1 over K plus G. Now when I take this, when the K becomes very large, then this will be very close to 1. Then I have good tracking. So we did not design the K in the frequency. We did not select the gain based on the frequency. We selected the gain based on this requirement. So if I want to have good tracking, I have to have the gain as high as possible. Okay. Now, here, if we look at the effect of the noise, if I make the gain as small as possible, then GK will be almost 0, and the denominator is almost 1, so the effect is almost 0. So for noise suppression, again, I have T is equal to GK, 1 plus GK. And if I take the limit as k goes to 0, then this will equal to almost 0, and I have good noise suppression. The last criteria now is the disturbance restriction. And I want S to be as close as possible to 0. So now, to make it as close as possible to 0, I'll make the k very high. So I'll take the limit of all this as k go to high. And this will become as close as possible to 0, and this will have good disturbance rejection. So now, to make it as close as possible to 0, I'll make the k very high. So I'll take the limit of all this as k go to high. And this will become as close as possible to 0, and this will have good disturbance rejection. Now, to combine all these in one chart, let me make here. I'm going to put here again the frequency, and then here on this axis the gain. And because I have a given system, I can also put here G. And I'm going to put the absolute value. Now I'm going to combine these requirements with this graph. This graph. We don't want to work at the high frequency end, because the high frequency end has all this noise. And also at the high frequency end, you will put a lot of power in your actuators, because the frequency is high, the velocity is high, for example, then you have to generate very high damping by the actuators. So we want to work at the low frequency end. At the low frequency end, I want to track and suppress and the disturbance, or reject the disturbance. So these two requirements are the same. At low frequency, where I can track the system, I need the gain to be very high, or I need GK to be high. And then at this end, if I want to suppress the noise, which occurs at very high frequency, then I need the gain to be very small. So I can have something like this. So at this end, I have the disturbance. At this end, I have the noise. And if I keep my gain high at low frequency, then I can reject the disturbance and have good tracking. I can make good vibration damping. And at this end, I can reject the noise and lower the actuator control effort, as we will see in 1 second. So here, this is the noise, and this is the disturbance. Now, all this you can only see all this in H infinity. Because all what we will try to do now is draw envelopes about what we like this to look like and about how this will look like based on what kind of sensors we have, what kind of disturbance we have. So by knowing the inputs that you have to go around them, then you can make envelopes. I don't need this to be like this. I can make it straight line and straight line. Get the asymptotes to it. So it can be very simple. And then generate my controller. And then the same here. I look at envelopes of characteristics. Okay, now I want to use these equations again to generate the controlled effort U at this point. How much this is. Okay. This classroom should have been the other way around so we can have more boards. But we have to redo these again. We have U is equal to K times E. And then E is given by this equation. E is YR okay, and then I'll replace Y from here. From this equation. And the Y is equal to T YR. Okay, and then minus T and V. This is plus, and then minus S and W. And then I'll group the terms now. So we have here K, 1 minus T, so this is 1. Minus GK, 1 plus GK, times YR. And then these two will be the same, will be minus 1 minus T, minus S W. Now I combine all this. And I'll expand the S also and make it 1 plus GK. Okay, so from this we have 1 plus minus, so this becomes 1 over 1 plus GK. The same here, and the same here. So I can factor all these out, and I'll have K YR minus V minus W. Okay, so now if you look at this equation, the control effort that we have is almost proportional to the gain K. So if I increase the gain, the control effort will increase. And this is expected, like in any system, if you have the same error, if you increase the control gain, then you have high control output. Then here, we'd like to have K as possible. Particularly at high frequency. Because at high frequency, usually the G's dies out. So at high frequency, the G dies out, the K is also small, dies out. So this whole thing is governed by the value of the K in the numerator. And reduce U. And for this reason, it is beneficial to have the gain as low as possible, especially if you are working in the high frequency end. Okay, now we will take this diagram and do a couple things on it. I want to shape the T and S in a special way so we can control them according to the design requirements. So I'm going to take this diagram. Then come here, make block like this, and then I call this Z1. And then come here, make a block like this. I'm going to call this Z2. I'm going to put here WT and WS. These are shaping transfer functions. This is used to shape the T, and this is used to shape the S. Why? I'm going to redraw this diagram in two ways. In the first way, we'll have G and K. And this is W T. And this is U and E. And I just leave this here, but I'm not interested in this. I'm interested in the effect of the noise on shaped output. Okay. I have, if you look at this diagram, here we have 1, 2, 3 inputs. Okay. And because this is linear system, I can study the effect of any input on any output, and then by the superposition, I can get the total picture. Okay, so now we will study only the effect of the noise on certain output. Okay, and then we'll redo this again by looking at the effect of the disturbance on another shaped output, and I shape it based on this. Is that what I want, or the other was key? Z1. Okay, and then so this is one way. And then the second configuration. We're going to have here Z2. And then W. Okay, and then we have G and K. Okay. So Y, well, this is WS, okay, so this is Y here. And now we'll have G. Flip these over. So I'll have K and G. Then the output will go to here. Okay, and then we have a negative sign in all this. Okay, now we'll write the transfer functions of these two configurations. For example, here, this is very easy because it's a closed loop system. Everything in the feedback loop and nothing in the forward loop, it is unity. So this is, everything is H. So the transfer function, because of negative feedback, I can replace all this by 1 over 1 plus GK. And then here is W. And then here is WS. And then here is Z2. And this is the sensitivity. Yes. So now from here, I can say, if I put a disturbance W, the effect of it will appear on this parameter Z2. And this Z2, I can write it as, again, WS times S times the disturbance W. Now, if I want to take this as one of the measures of performance, then this measure of performance has to be as small as possible to reject the effect of the disturbance. So I want to make this multiplier as small as possible. So this now would say that I have to have the absolute value is as small as possible from 1. Or the S absolute value is less than WS in inverse or vice versa. Okay. Now here, we can do the same and get the manipulation so we don't waste too much time. I can write this, the transfer function becomes Z1 will equal to minus WT times whatever we see at this end. Z1 will equal to this term times whatever we see from this end, which comes from V. And this will equal to GK times V. So accordingly here, this will equal to Z1 and V, and the multiplication is WT, and this is T, and then we have negative sign minus. And again, if I want to know the effect of the noise alone on a measured performance index, I want this transfer function to be as small as possible, okay? And from here comes the H infinity. Now I want to make this magnitude of the maximum as small as possible. Same here. I want to make the amplitude of this maximum as small as possible, okay? When I do this, then I'm rejecting the disturbance by measuring a performance index, Z2, and if I make this as small as possible, I'm rejecting the noise by making the performance index Z1 as small as possible. So now, this from here, we get the same approach, that T should be less than WT inverse, absolute value, and absolute value. Now, to summarize all this, I don't need this anymore. This is the frequency again. S. So we have this characteristic, so we can reject the disturbance. And then here, this should be like this. So we can reject or suppress the noise. Now this T has to be lower than some transfer function. I will select this transfer function. Okay? So I'm going to select this to look like this. Has to be lower. So my transfer function might look something like this. This is very easy to represent as your design requirement. Okay? Same story. I have to have S lower than the inverse of WS. So this is the inverse of these two functions. Now I can plot here these two functions. This will look like this. And then this will look like this. This is my WS, and this is my WT. Now again, the whole thing comes from the requirement that I like to reject the noise and I like to reject the disturbance. I don't know what S look like and I don't know what T look like because S and T, both of them depend on K, and that's what I like to extract out of this whole thing. Now, we want to do this in two ways. We want to relate this to system stability, how we selected the system stability, and then the second thing, how to relate this to uncertainty in the G. Again, everything is available only in the H infinity approach. I can look at effect of disturbance, I can look at effect of noise, and the third thing that we will add now is the effect of uncertainty. I don't know G exactly. I don't know G exactly. G can be G plus some delta G. And the delta G can come from mathematical modeling, as you will see in the example that we'll give, or it comes because of the performance. The structure is in one place now, and then I have one payload on it here. So it has natural frequency. If I move this payload here, it has completely different natural frequency. How much this payload will move will define how much the transfer function of the structure will vary. If I have a rough idea, then I can say within 10% or 20% or 30%, I am uncertain about this G. Once I put this, then we can design the controller to work for all this range. You cannot do this with any of the classical method that we covered before. So we have three things that we will try to do. Reject this, or suppress this, reject this, and then accommodate parameter uncertainty of the system. Okay, and I'll do only one way of defining the parameter uncertainty. Say here system uncertainty. There are two ways of doing it, and I'm going to use multiplicative uncertainty. There is additive uncertainty, but we can show that the two converge, and it's very easy, but we'll cover only this, and the same applies to the other case. So for example, if I have a true transfer function, I can represent this like this. Either like this, this, I can remove and I put it in a box. And this box multiplies the transfer function of the nominal system. So again, if I have the payload here and then it moves to here, I can take my transfer function nominally here. So I have some here and some here. I don't have too much deviation. Half of it, I split it between these two places. So I have a nominal transfer function. And then I describe the uncertainty in this way. Or I can take this box and put it on this side. It's the same. This is mathematical representation only. And we will see how to do this with the finite element. So now I have this, I can write the true transfer function in this form. So I can write G. I have U going directly. And then U multiplied times delta M, and then add it to it. So this is in effect 1 plus delta M. So I can put this one times G. Now in this form, it looks very nice and clean. My system nominally 100% here. 5-10% deviation here. So this is the amount of uncertainty. So del M is the amount of uncertainty. Okay. Once we write it like this, then we can also see the other form, which is the additive uncertainty. So I have G is here, plus delta mg, which is an additive uncertainty to this G. The two look the same, but mathematically they divide them and then they follow different routes to do the proofs. But this is good enough for us, okay? So now...
can delta M be positive or negative?
Yeah, but the bound on it is, we'll say, 20%. Plus or minus, we'll just see the absolute value of delta M is 20%. And we'll show you when we do the finite element. Of course, will be some positive, some negative, but we'll do the absolute value, and I'll bound this absolute value by a maximum like ignorance level and system characteristic. Okay. Now, I'm going to redraw the structure that we did before. Now, we'll incorporate all this. Del M into the system closed loop. And I have here a sheet. We can before this, just make here the typical system will look like this. G delta and then I'll break this G delta using either this configuration or what I'm going to have here. And the reason for putting it here, if I take this whole thing and collapse it, this affects the output. So this acts as a disturbance on the system. So I can look at the uncertainty as if it is part of the W of the system. Okay? Now, to do this, I'm going to take this line and make it green here, and then green here. And then the rest is like this, orange and orange. And then I'm going to break this line here and here. So this is almost like a free body diagram, okay? And then now I have this, which is the effect of the uncertainty, looks like a disturbance. And I'm going to call this I, input. Okay? And then this is my output. And I'm going to look at the transfer function between these two. So I'm going to eliminate this. So I look only at the effect of a single input on a single output. Single input and single output. And I reduce this whole thing into a single block. Now, the input, it comes here. This is the output. So this is output also. So the input plus output times k minus times g is the output. Okay, so now I can rewrite this as the input plus output times gk, and it is minus, is equal to the output. And then now I'll group the input and output and get the transfer function of this entire box. So I have again 1 plus g k, and out is equal to minus gk and in. And then the relationship between the output and in and it is minus. So we can call this, for example, any name, M, for example, and in and out. This box now, I have between the relationship between the input and the output is this M. So I can remove everything here and reconnect these lines again with the box that has this transfer function M connecting them. So this will look like this. Okay, and then I don't need all this. Now we'll go back to what we've done to study stability. I have to have one del M M as far away from the equality. Okay? As far away from the equality. Again. Del M M is given by this curve. And I like to be from this point as far away from the one as possible. Then, for stability, I don't want this equality to hold. Okay? So now I have to have del M. M is much smaller than 1. And of course, this has to be the absolute value. Okay. I can also look at del M and M. Absolute value. This is less than the absolute value of del M, the absolute value of M. And I want this to be less than 1. Okay. Now, this M, I should not write it as M, because this M absolute value is nothing but the T. It's nothing but the T. So I just put this minus this as M, but I should write it as minus T. Okay? So now from here, well, I can put it here. But the absolute value of M is nothing but the absolute value of T. And now for stable operation, this absolute value of T should be less than the 1 over the absolute value of del M. Or del M is greater than, less than 1 over absolute value of T. Now I can add one more thing here. We'll say here on the side, if del M is bounded by some positive gamma. This is the uncertainty level. Then now I can say to select my controller in here, to select my control gain, K, I have to have the transfer function is less than or equal to the reciprocal of the uncertainty. The reciprocal of uncertainty. So this is equal to 1 over gamma. So if I know the level of uncertainty, then I have a bound on my transfer function, and then I can get the K. This K, because of this fact, this stability is called the small gain theorem. Why? Because for any system I can write this as 1 plus G K, or if we follow the same procedure here, then I have G K is less than 1, and then K absolute value will be less than 1 over G. Okay? So now the gain has to be lower than the absolute value of the transfer function. So this idea, just satisfying the stability, is transferred to what is called very famous theorem, which is called the small gain theorem. So to treat system uncertainty, we can use the small gain theorem. Okay, we covered an awful lot of grounds today. Awful lot of grounds. You can see this in a couple minutes, how you can use this to design the system very fast. So now, the first line says, if I know the amount of uncertainty, I can design my controller gain. Okay? The second line says, if I have certain closed loop system, how much uncertainty I can put in the system before the system goes unstable. So here it says the uncertainty that I can accommodate with a given controller has to satisfy this inequality. Okay, so these are two ways of looking to the same problem. So the bottom one, for a given G and K, for a given system and a controller, how much uncertainty we can accommodate before becoming unstable. This inequality states the maximum bound of the uncertainty beyond which we become unstable. This inequality states the, or defines, system uncertainty that this controller can be used before the system becomes unstable. The second system, the first one is the open loop system uncertainty. The second system is the closed loop uncertainty. The closed loop becomes unstable. So here is open loop. And this is closed loop. Becomes unstable. And then here, for a given bound on system uncertainty, gamma, this inequality defines the control gain limits before the system can become unstable. For a given bound on system uncertainty, gamma, this inequality defines the limits on the gain k before system becomes unstable. How we use all this? We have 7 minutes, but we'll try to do something. Two. Okay. Don't sit on, please, huh? This the handout that you have is a very simple case that illustrates a lot of things that of what we're trying to do. Now the example that we have, I have the same rod that we used was H infinity and H2. I have a rod that is divided into two elements. And this rod length is 1 meter. And EA is 1. M is 1. One time, I'm going to take this structure and divide it into two elements. Okay? And then in another time, I'm going to take the same structure and say it is only made of one element. One element. Okay, and that's typically what we do in finite element. I either have a good model or a coarse model. Okay? Okay? Of course, this is not good, but it's good enough for us to see the example, what will happen. Okay? So I'm saying this, I'm calling this high order model. And then this is a lower order model. So now I look at the two element or the single element. Okay? Now I assemble the stiffness and mass matrices. Once we have them, I can go and get the A, B, C, and D matrices. Everything is defined now. Okay? Or I can make this whole thing one element. So the stiffness and mass matrices are just the scalar values, and then I assemble everything, and I have the A1, B1, C1, and D1. Now I have the A, B, C, D. I go here and calculate the numerator and the denominator using the state space to transfer function command. And then plot the Bode diagram, which is the magnitude of the transfer function and the phase for the high order and the low order system. And then plot these. Okay? And then I'm going to plot also, the plotting are messed up because I plot all these results with the same program, okay? But what we want to do is, I'm going to plot the magnitude of the original system and the magnitude of the low order system against each other. Against the frequency on the same graph. Okay? And I will also plot here this parameter. Okay? This parameter is 1 minus the magnitude of the original, of the reduced order, divided by the magnitude of the original system. So if you look at this, and this, which I did not erase on purpose. Now if you look at this, this will be G delta over G minus 1. This would be G delta is equal to G del M and G And then now I want to extract the del m. So the del m will equal to g delta minus g over g. And this will equal to g delta over g minus 1. Okay? So now I'm going to plot here this ratio, 1 minus the ratios of the g's, delta g's. Okay? And then now, so I have plot of the system, transfer functions, and then the uncertainty. Okay, so if you look down here, the red is the high order system. It has two elements, so it has two natural frequencies. Now I simplified the system like this. So it has only one peak, and then there's nothing here. Now if you look at the difference between them, difference here is positive, difference here is negative, but the absolute value, I'm plotting it here. This is the absolute value of the uncertainty in a dimensionless form. Dimensionless form. So this is delta M. Now I want to design a controller. I'm going to design a very simple controller. This K, I'm just taking it as a constant, proportional controller. This is a proportional controller. And I'm going to draw two graphs. I'll show you what we have and then we'll describe it next time. But the two graphs that I want to show, this graph, which is the root locus. The root locus. This is a proportional controller. I have four poles in the high order system, or two poles in the lower order system. I have second 2 by 2 matrices in this case. Here I have 4 by 4 matrices. So I have four poles. Now if you look at the zero line is right here. So the pole, if you remember, has gain is equal to 0. And then I'm trying to look at where the zeros are. I don't have any zeros, so I look at them at infinity. So I start from here, and then I go to infinity. Start from here and go to infinity. This is two branches. These two branches start stable until they cross this line at gain higher than 0. They become unstable. But these two branches, for any gain, are stable. So now, accordingly, this higher order system, I just cannot use any control gain because at higher gain, it will cross this line and becomes unstable. Now, if I simplify the system like this and design my controller, that's the root locus. Everything is on the left-hand side. So this gives me wrong information. Wrong information. I simplified it very much that this says use any control gain. Use any control gain. But I cannot use any control gain. Okay? Because I have now uncertainty. This is the exact model, quote unquote, and this is the very approximate model. So there are errors, uncertainty between them. This uncertainty bounds how much gain I can put on the system. Okay? Now, how would we do this? I'll just show you the last diagram, and then we'll describe it next lecture. And this last diagram is right here. It's right here. I have to have the uncertainty, absolute value, smaller than 1 over t. 1 over t. This is 1 over t. 1 over t. Okay? Yeah. No, I flipped them over, I'm sorry. Yeah, I'm sorry. The 1 over t should be lower. Yeah. Yeah, okay, it's fine. Yeah, it's fine. Okay, because the t has to be lower than 1 anyway, so the 1 over t is this line, okay? So now, this is the 1 over t. This is the delta m. Now, this drawing is done for gain of 0.1. K is equal to 0.1. If I take the gain higher than 0.1, then this line goes under and the stability requirement is violated. Stability requirement is violated. So now, in this form, now we can see where is the uncertainty in the system parameters are, how we select a controller gain so I will not become unstable if I have an upper bound on the uncertainty. Okay, we'll describe this in, next time in more detail. Have a good evening.